Hello everyone and welcome to the digital structure tutorial number 2. In this tutorial I will explain how to build a basic model using beams and plates. Before we proceed, I'd like you to notice that there's a global coordinate system in the middle of the 3D window. It has 3 axes and an origin, which is hidden right now. We will use it to position and orientate our objects. Let's start by creating a plate. As you can see, there are several plate sections available. Let's choose the rectangular one. This plate is defined by a few parameters, such as h and b, which can be modified. We can also change its thickness and yield strength. Now, if you look at the plate, you will notice that it has an internal coordinate system. To orientate the plate, we are going to match its internal axis with global vectors. One of the internal axes has a special status, indicated by a black highlight. It is the primary axis and it can move anywhere in space. The 2 other axes are considered as secondary axes. They can only move in a plane perpendicular to the primary axis. All of the axes have 2 opposite parts, which can be moved to orientate the object. Let's start by aligning the primary axis with the global z-axis using the left mouse button. At this point, the secondary axis can only move in the xy plane. It is also possible to change the primary axis. If you want z to become the new primary axis, all you have to do is double-click on it. Now, x and y can only move in the yz plane. Let's go back to the initial orientation. You've probably noticed that when I hover over the plate, its internal points become visible. These points are used to position the plate by matching them with a global point. Here, I will position the plate on the origin of the global coordinate system. Alright, let's confirm this orientation. More often than not, the global coordinate system is insufficient to position and orientate our objects. To remedy that, you can create your own global points and vectors. Let's make a single point, defined by coordinates 1, 0, 0. Let's make a vector, defined by coordinates 1, 1, 1. As you can see, the 2 objects appeared in the history after the plate, which indicates their order of execution in the script. To edit the plate's orientation, click on the Details button. Here, we can see all the data used to define the plate. Let's click on Edit Orientation. If we move the plate around, it will appear that we can't find the objects we've previously created. That's because they were created after the plate. We can fix this by moving the plate down the history list. You can see that the script has been modified and re-executed. It's now possible to edit the plate, position it on the new point, and align its primary axis with the new vector. If instead we use a secondary axis, the global vector will be projected on a plane perpendicular to the primary axis, and that projection will be aligned with the secondary axis. Let's confirm and add a new beam. Beams are classified by catalogs, the European catalog being the most complete, and by section types. Clicking on a section opens a list, which can be filtered, so you can easily find the section you're looking for. Let's choose an IP 100. The default length of a beam is 1. To change it, we can modify the input value, or we can stretch the beam by left-clicking on the black cone at its end. Now, if we hover over the plate, we can see that its internal points have now become global points. Let's try to position the beam relative to the plate. This time, we're not going to use a global vector to orientate the beam. Let's left-click on the arrow at the end of the internal axis and direct it towards one of the plate's points. This is an alternative way to orientate an object. Let's do the same with a secondary axis. Initially, I positioned the beam right in the middle of the plate, but let's say that I wanted to position it somewhere else. I would have to confirm the current orientation, create a new point, change its position in the history list, edit the beam, and finally put the beam on the new point. This would be tedious. Instead, we added a feature that lets you create objects, that is points or vectors, which are local to the beam. All you have to do is grab the beam, and the top of the interface will switch into point creation mode. Let's define a point as a middle of 2 points belonging to the plate. The new local point is shown in blue, and if we confirm its creation, the beam is going to snap into its new position. So the beam's position and orientation are entirely defined by the plate. It means that if we change the plate's orientation, like say realign a secondary vector, the beam's orientation will be modified as well. Now let's add another beam. This one will be an angle. Let's position it so that it's in contact with both the plate and the beam, and align it with points belonging to the beam. Now let's shorten it to make it just as long as the beam's web. If we decide to change the beam's section to, let's say, an IPE 200, the angle will become too short. To avoid that, we can edit the angle and stretch it towards a point at the bottom of the web. And as you can see, the length is now defined by a point instead of a number. If we edit the beams section again to an IPE 160, the angle's length will adapt. As you were able to witness, Digital Structure has some powerful tools that make joint design quick and flexible. The next tutorial will show you how to make an intermediate model featuring bolts and welds. See ya then!